Good afternoon. We are pleased to welcome you to the Washington Labs Academy webinar series. We hope you find the next hour or so useful and informative. We have developed our webinar series to deal with some of the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. Before we begin, a few housekeeping details. First, I hope everyone can see the title slide on their computer. A recording of this presentation will be sent to all attendees. A full screen view may be preferred. Your selection at your computer can be done by using the menu panel in the menu on your screen. You'll go to View and then select Full Screen. We do estimate that the main bulk of the presentation will take approximately 1 hour. There will be an extensive amount of material being covered today. Should we not get to your questions, please send any questions or comments related to this topic to questions@wll.com. If you'd like a Roden Swartz expert to contact you for a demo, or if you have more questions related to a project, please indicate that in your email. Make sure to include your name, your company, your email, your phone number, and zip code. And now, I'd like to introduce our presenter. Jeff Solomon has more than 3 decades of experience in the test and measurement industry with roles in application engineering, product specialist, sales management, and distribution management. For the past 8 years, he has specialized in EMC, focusing on over-the-air, antenna test, and Tempest for Roden Swartz. So, without further ado, let's turn our attention to 10 reasons it may be time to update your MIL Standard 461G test capabilities with Jeff Solomon. Hi, Jeff. It is all yours. Take it away.
Hello, my name is Jeff Solomon. I'll be your presenter here today on this webinar talking about the 10 reasons it may be time to update your MIL 461 lab. Before we get started, I really wanted to thank our hosts at Washington Labs for helping us put this webinar together. And we have been able to do a couple of these with Washington Labs, and we do enjoy working with them and their support. I've been doing EMC and EMC systems for 10 years at Roda and Schwartz. And as I've traveled throughout North America, I have seen some opportunities perhaps to do things a little bit differently, maybe to speed things up perhaps, and look at doing testing a different way. And we thought it might be helpful for everyone to present some of those ideas in this webinar. So thank you for joining. There will be a Q&A session at the end of this, at the end of the webinar. So feel free to stay for that. And you also, I believe, can ask questions through the chat. So welcome, and let's get into it. So certainly our topic today is MIL Standard 461 testing. But I just really wanted to briefly touch on the fact that there are many standards out there being outside of MIL Standard. Some are similar, like DO160 is somewhat similar to MIL Standard 461. The limit lines are different. The frequency coverage is different, yes, but DO160 doesn't indeed require a test table inside the chamber, and really all the tests get done on that table. CISPR 25, which is an automotive standard, has a test table inside a chamber. It's a chamber that's similar in a lot of ways to the MIL standard chamber. So there's commonality in those in those types of approaches. Certainly in the commercial world, chamber size is much larger, and the height requirement inside the chamber is different. But the commonality is the 4 groups of tests are the same. you need to pass both radiated and conducted emissions, and you need to have your equipment operate within the fields associated with that industry, the field strengths for conducted and radiated susceptibility. So that way everything is common. Obviously the overall frequency coverage in test equipment definitely can change. So everybody has to pass the EMC standard in whatever industry you're in. And our goal is maybe to give you some ideas on how to do that a little bit more effectively. So, just continuing on with our topic of MIL Standard 461 testing and some reasons to upgrade your lab. There was a change to the standard in 2015. Now, many labs that I have traveled to in North America are still on standards E and F. Previous revisions to the standard, but just about everybody eventually is going to have a project with 461G, and of course many are in the middle of 461G testing. So just to outline some of the changes, the major changes, we're adding of electrostatic discharge testing, ESD testing, and lightning testing was also added. But for many, maybe the most important change was the allowing of an FFT receiver to be used in emissions testing. So we're going to spend some time on the EMC receiver and FFT testing as a way to really improve productivity in your lab. And we'll talk a little bit about the technology that's behind it and really the added benefits of it. So we mentioned the FFT receiver in the previous slide, and let's talk about the technology that's in the FFT receiver that allows it to exist and help reduce scanning times. So in its simplest form, you could think of the technology here, time domain scan, as a way to take an overall spectrum, break it up into certain smaller bands that you see in the upper left-hand graph. Within those bands, we do a high-speed frequency sample and sample each frequency interval. Then do an FFT to get the frequency domain back and stitch it all together to get an overall scan. So this technique has been around for 15 years in terms of a commercial product. It's a mature technology at this point, and as of 2015, was made available to the MIL standard world in revision G. So time domain scan, we'll talk about in terms of the speed improvements that are possible. Certainly a technology you want to think about in your next receiver. So one of the other technologies now that are available in a modern receiver is a real-time spectrum analyzer. So real-time spectrum analysis is not applicable to MIL 461G in terms of emissions testing that you're going to publish. That is not the intent of this function in the receiver. It is really meant to be a troubleshooting, debugging tool that's available for post-scanning, so that when you find a problem, you can go ahead and do some better analysis on it. So I want to make that clear. This is a debug tool only, not to be used for standards testing. But it is a very powerful tool. And I also find that many people confuse the real-time spectrum analyzer with the time domain FFT receiver, and they are definitely not the same. So this is a mode of operation that can look at things in real time in the spectrum. You certainly can take your results of a scan that you do in time domain and then focus on disturbances you may see in the scan with the real-time spectrum analyzer and help you debug what's going on. And that's really the intent. And in fact, many labs have found this very, very useful. A lot of Mill Standard 461 labs are working on prototype kinds of projects where a lot of unknowns are maybe going on, and something like a tool like a real-time spectrum analyzer can be of real benefit in that kind of scenario. Again, not to be published in a test report, in terms of passing the standard, but certainly a great tool to use when you're in the middle of a test and you cannot figure out why you're failing. So we've kind of gotten a little bit of technology discussion behind us in terms of a modern receiver and what kind of functions may be in it. But let's look at what that really means in your lab. What does it really do for you? What does the FFT mode really help us with? And maybe focus a little bit about some of the other added value in a modern receiver over a spectrum analyzer, if you're currently using a spectrum analyzer for emissions testing, and then maybe extending the measurement capability beyond the traditional band and at 40 gigahertz, perhaps all the way up to 500 gigahertz. All of this is possible in the modern receiver. Let's touch on each one of these. So in the previous slides, we've talked about the technology that enables the FFT receiver, but let's have a little discussion about what that really does in your lab. So, in its simplest form, I think if you think about the FFT receiver and what it does for you, and its fast scanning capability, what that really means is the ability to capture the intermittent emission. It's increasing your probability of intercept of the emission. And so, that capability is often critical and often what is most wanted out of a receiver. If that emission that is either exceeding the mill standard limit line, or perhaps that emission is affecting the operation of the EUT, to capture it can often be very, very critical. And so you couple that with the high frequency resolution you get in FFT mode, 2x improvement in the amount of sample data that's available, higher frequency resolution over a classical EMI receiver scan, or even more data than what a spectrum analyzer sweep would offer. So increasing the frequency resolution, and then because of this fast update, we now can make some adjustments to the EUT. Perhaps load a new level of firmware or make an adjustment on it and see if that affects its ability to get under the limit line in a quicker fashion. And then if we think about the diagnostic angle with the real-time spectrum analyzer, now we have two tools, the scan that you would use in a classical sense for the test report, but now a diagnostic tool with a real-time spectrum analyzer to be able to tune to a disturbance you see in the scan and really figure out what's going on at that point, and then measure things like turning on a spectrogram and measure frequency as a function of time, and also turn on perhaps a persistence mode in the real-time spectrum analyzer so you can see things like signals under signals that may be causing an issue. All this kind of capability is available in the modern receiver. We should be able to see a short demonstration of this in the following slide.
So now let's talk about what is possible with the real-time spectrum analyzer. So you should be seeing a example of the real-time spectrum analyzer in use. In this case, it's a keyless door entry into a car, and you can see the initial event, and then also see how that kicks off a series of other events within the vehicle that the antenna is picking up. So if you think about when you go into a car and what happens, and you do your keyless entry, and then you go into the car, and perhaps lights turns on, and perhaps the electrical system as a whole turns on, depending on what's the feature set of the car, you can see how that whole sequence of events is captured in this display that we have with the real-time spectrum analyzer. And the waterfall display gives you that display of frequency as a function of time. So you see the persistence mode of the spectrum analyzer showing signals underneath other signals, and then also the time capture of the spectrogram. This to me is the ultimate diagnostic tool that you would have available in the modern receiver to help you hunt down potential problems that could be existing in your designs. So real-time spectrum analysis, very cool and very functional capability in the modern test receiver.
So let's talk a little bit about the actual reduction in measurement time that we would see with an FFT-based scan. And the table below is outlining a couple of different scenarios here. We have the frequency band, the resolution bandwidth, the actual analog time for a sweep, and then what the equivalent FFT dwell time would be, and the time for the FFT scan to get done. And you can see the dramatic speed improvement over each of these scenarios of the analog sweep versus the FFT time. And so, that time directly relates to productivity in the lab, I think. And then even if you lower the resolution bandwidth and add longer dwell times, that time savings actually goes up. And you do all this with no sacrifice of dynamic range. You have great dynamic range with an FFT. It's actually the same dynamic range with the FFT receiver over a classical EMI receiver. So these benefits are realized with the modern receiver. So let's take another example of basically reducing your measurement time with a FFT receiver. In this case, we're looking at the S121 standard, which is a space standard. If you're not familiar with it, it's based on the MIL standard, that has some challenging emission requirements, certainly a challenging limit line that we see here, with some notches in there that will require dynamic changes in the resolution bandwidth. And if we look at a scan like this, this is a challenge for an older technology like a spectrum analyzer to be able to do in a quick kind of way. And you look at the resolution bandwidth table that's on the left-hand side, and we look at what a 10 hertz resolution bandwidth scan would take that may be required for some of this testing. You're looking at 4167 hours versus 4.2 hours with the FFT receiver. So that's an incredible reduction in test time, and can save you weeks in the lab to try to qualify a product. So just another example where the FFT receiver can be extremely helpful. Okay, so let's talk about point number 3 in our list, and this one concerns the modern receiver again, and preselection. For those who may not be familiar with preselection, you can think of it as a bank of hardware filters that are in the front end of the receiver. They are switched in and out as the receiver tunes through its specified scan. And so, by switching in and out these filters, you can think of them as bandpass filters. What we're doing is helping to eliminate as much as possible the out-of-band signals hitting our mixer. Now, this is something that many people don't realize with the spectrum analyzers. With the spectrum analyzer, all frequencies hit the mixer that are presented to its front end. There's nothing to filter that out. And so the preselector, by filtering out the out of band, can prevent an RF overload. And obviously an RF overload would be an invalid scan. We can't have an RF overload light published in a test report. So that's a real time savings, and it also prevents really just a bad scan from happening. We'll show an example in a following video of having the preselector on and off, and the differences that you'll see as a result of that. Now, in order to do this, we had to go into spectrum mode on the receiver because that allows us to turn the preselector on and off. That is not possible in receiver mode. So let's take a look at the video.
This video demonstrates the value of preselection in an EMI receiver as opposed to a spectrum analyzer. Here we have a CISPR pulse generator input to a receiver, but the receiver is in spectrum analyzer mode where you can enable and disable the preselector. So this sweep is with the preselector off from 400 MHz to 1 GHz. Notice that there is no overload indicator. This is because the overload indicator cannot respond fast enough to a small duration pulse from the pulse generator in CISPR. Now we're going to turn on the preselector and sweep the exact same frequency with the exact same input stimulus. Notice that we get vastly different results. Without the preselector, the receiver was overloading. It just didn't know it was overloading because it could not respond to the pulses fast enough. In the preselector on case, it's not overloading and you get the correct results.
Okay, good video on preselection. I hope everyone enjoyed that. Let's talk about the future a little bit. Let's talk about 5G, a technology that's coming certainly very fast, if not already here. This is definitely a technology that will be dual use. It is being talked about as a technology that the military wants to embrace. And so 5G has some unique measurement problems that it presents. And certainly if you think about carrier frequencies above 39 gigahertz, even, some new bands are opening in the upper 40 gigahertz area. This is near the end or beyond the reach of the modern receivers, which stops at 44 gigahertz. So how do we address those kinds of applications? Well, you do it by being forward-thinking and configuring your receiver with the capability to use external harmonic mixers. And there are harmonic mixers out there that they go all the way out to 500 gigahertz. There's even some newer types of approach with subharmonic mixing with an integrated antenna and preamplification that can offer reduced noise floor over traditional harmonic mixing techniques. So be forward thinking when you're looking at your next receiver, configure it for harmonic mixers, and give yourself some insurance that you can see intentional radiators beyond 44 gigahertz. All right, let's move on from the modern EMI receiver and talk about automation and what automation may be able to do in your lab. Three items we're going to talk about here: the use of a modern 64-bit EMI software, some things that the mill standard asks for in the EMI receiver, and then coupling your EMI software with the use of a visual and audio inspection tool to help make sure that you indeed capture when you have a fault during a susceptibility test. So let's get into these. Okay, continuing on with our discussion about reasons to upgrade your mill standard 461G lab. Why don't we look at software? Software is something that most customers use, although there still are customers out there who do a lot of manual measurements. And so the use of software obviously can add in add in repeatability for measurements, add in obviously some speed enhancements as well, especially in the area of taking in these large amounts of data and reducing it down to signals of interest. But what if we could do that in a faster way? Well, most of the software out there is 32-bit. And if you invest in a modern software, at 64-bit software, you can take advantage of that extra processing power and speed up the calculations that are done in the emissions piece of the software. And also, how about something that's a little more user-friendly in terms of using things like a database type of structure where you can easily search for things like limit lines and transducer factors and quickly add them or remove them from a test. And then also, how about taking that software and having it interface with something along the lines of a visual inspection or audio inspection software for immunity testing? All these kinds of things are available now on the market with a modern 64-bit EMC software application. So important things to think about. This is probably one of the least expensive upgrades that you can do for your lab. Let's continue on with the automation topic and look at a simplified way to set up an emissions test. And this is in the modern test receiver. In the past, you've had to set up, if you're using spectrum analyzers, you needed to calculate the sweep time and the number of points in order to make sure that you were dwelling long enough over a frequency to meet the standard, or perhaps meet the dwell time that's required for your EUT. And so that manual calculation is adds in the possibility of human error. So one of the things that the Mill Standard Committee kind of insisted on was the ability to enter in a lot of those parameters directly into something like you see on the right-hand side of the slide, where you could directly add in the range start and stop and what the measurement time is for that particular range. And obviously that's important because that measurement time changes as the frequency range changes. So having the ability to directly enter in that amount is critical. And obviously that what you see in the table 2 is the minimum amount, not the what may be required for your EUT, which obviously could be longer. So this eliminates the concerns about configuring a non-compliant test and ensures that you maximize the total time and making sure that the point of interest is acquired in the shortest amount of time. So kind of a simple technique, but pretty powerful. Okay, let's talk about enhancing some susceptibility testing. It's part of 461G. I've seen labs where a operator basically watches the EUT, and in this test, as many of you should be aware, that some of these susceptibility tests can take a very long time. So you're watching a monitor, and you're seeing if the EUT does some sort of action that it shouldn't. Maybe that is a character changing on the screen, or perhaps it's a light turning on, or a light changing in intensity, a gauge moving. Those kinds of visual inspections to be done by a human operator, are fraught with error. As humans, we can't stare at screens and be totally focused on it 100% of the time. And so certainly having a tool to be able to do that can really be important. Also, let's talk about reducing some setup complexity in CS114. Maybe talk about the use of a digital oscilloscope, a modern one with some different probe technology to do CS101, and the use of smart broadband amplifiers for a susceptibility test. Those are the topics we're going to be touching on. So I mentioned in the previous slide the ability to do visual and audio inspection of an EUT. And if you think about it, you're certainly measuring the field strength while you're doing a susceptibility test, or measuring the current if you're doing an injection test. But ultimately, we're looking for the reaction of the EUT while that field is present or that current is present. And what is the EUT doing? Is it immune to the field? Does it act as it should while that field is present? And so how do we do that? Well, in lots of cases, you can do some monitoring via data lines from the EUT to some sort of monitoring capture device outside the chamber. That's commonly done. But if you have to do visual inspection, the only real safe way to really do that is to have a camera system inside the chamber for radiated susceptibility. So, when you have a camera in there, certainly you can have a screen present and look at the EUT for changes while the immunity test goes on. But as I stated before, you can't guarantee you can monitor that as a human 100% of the time. And then some of these tests can take very long. The dwell times, can be seconds on some EUTs, and of course you've got to go through a full spectrum of frequencies. So that can add up to a very long test for a human operator to be monitoring an EUT. So if we had the camera system, but not add in some software, some capture software, where you could continuously monitor 16 to 32 regions of interest within the screen, and then track things like changing of characters or lights turning on and off and such. Now you have a real powerful tool. You couple that software with your EMC software running concurrently, and now you have the two tools talk together. This really does create an environment where it's a completely automated kind of test for susceptibility. So, we're going to have a video that shows some of this capability in the cockpit of the 737 with gauges turning on and off, just to get an idea of the type of monitoring that can be done.
This particular video is a flight simulation of an attempted landing, but you can use your imagination that we could suspend an aircraft inside the test chamber and see what happens to all of the ROIs when a large field strength is incident on the aircraft. For today's example though, I'm manually and purposely causing the ROIs to change just so that you can see them in action. So what exactly are we looking at here? Well, actually several things. We're using object in and object out ROIs to detect if the landing gear lever is moved to the up or down position. And in conjunction with that, we're also using light on ROIs to monitor the landing gear status whenever the lever is moved. In this video snippet, the landing gear lever was moved to the lower position right before recording began. And landing gear, of course, takes a little while to get set into place, so keep an eye on the status light to change as you go throughout the video. Moving over to the left-hand side of things, we're using an intensity change ROI to determine if the below glide slope indicator turns on. This indicator is something that tells you that the aircraft could be on a bad trajectory for landing. And by now you've seen an entire loop of this video, you know that the landing didn't go very well. The cockpit certainly gave clues that this was going to happen, especially with an indicator just like this one, which is currently turned on, as you can see. As you go through the video, you can keep an eye on this. You'll see that that indicator turns on shortly before the plane crashes, which is right about now. Last but not least, we're also using OCR number ROIs. This is the first time you're seeing this particular ROI in action, so let me share some more details. In this case, we're monitoring for a few different readings within the cockpit. But if you focus on the leftmost OCR number ROI, we're looking at the current airspeed within the primary flight display area. And with the OCR number ROI, you can define a range of numbers you'd like to monitor for. You can tell ADVISE that an event occurs when a number sits inside of a defined range or outside the range. In this particular case, we define the limits to be plus or minus 10% of the currently defined OCR value of 220, which equates to a range of 198 to 242. We also tell ADVISE we want an event when a number sits outside of that range. That means that if we see anything below 198 or above 242 during our test, the ROI border should turn red, which is something we're seeing now. I'll let the video play just a little longer so that you can watch out for a few of the things that we just discussed as far as what's being monitored for. I'll also take this time to mention once more that with the possibility of monitoring up to 32 different events simultaneously, ADVISE allows you a lot of flexibility as to what you can monitor for. As evidence in this example, there are many lights, colors, numbers, text, and analog indicators that you can watch for in the cockpit depending on certain conditions. And as I'm sure you can imagine, there's an incredible number of combinations as to how you could specifically set up your own particular ROIs in a test setup.
Let's think about one of the individual tests that have to be done in MIL Standard 461G, and that is CS114. CS114 in the commercial and automotive worlds is known as a bulk current injection test. Basically, you apply a current to something like a wiring harness with a current probe and inject the current onto the wiring harness, onto the EUT, and you do that over frequency at a certain amount of current. And in MIL Standard, there's a table that's a graph that's published for different curves indicating how much, depending on the type of EUT it is, you would apply the correct curve. And so, interestingly, if you think about CS114 and the curves that you see there, curves 1, 2, 3, and perhaps 4 do not require a lot of power from the amplifier. And in fact, a modern signal generator with an ultra high power option could deliver enough power perhaps to get you to curve 4. Certainly, if you needed to get to curve 5, you definitely would need to take a more traditional approach with a signal generator or some power monitoring devices and a power amplifier. And that's also what you see here. But the approach is now we rack it all together. We rack it into one piece. This is our CS114 test set. You then hopefully would run that with a modern 64-bit software that will, in our measurements, definitely speed up the test over previous legacy EMC software. So some different approaches to CS114 to help reduce test setup complexity and accelerate your test times. So let's look at another test within MIL Standard 461G, CS101, that's been a challenge in the past. A lot of labs out there are using older digital oscilloscopes, or perhaps even an analog oscilloscope, to make this test. And why not think about a new approach with a modern digital oscilloscope? And so you think about CS101. Typically, you have to make a differential measurement, and the way labs in the past have done this is by floating the oscilloscope and losing its reference to earth ground. In some cases, this might be absolutely necessary, but why not think about using a differential probe for that purpose and making the measurement safer. So when you float the oscilloscope, you bring the voltage potential of the measurement to the outside of the case of the instrument, which obviously is a hazard to the user and a hazard to the instrument as well. So using a differential probe will allow you to safely make the measurement. And then you have the capabilities of the FFT within a modern digital oscilloscope, where you can do thousands of FFTs a second, and give you, with the high definition mode available, with the oversampling techniques that are in the newer digital oscilloscopes, give you up to 90 dB of signal to noise ratio. So, and that often will give you the ability to see things that you perhaps can't see the injected signal in this case much easier. And also, obviously, an oscilloscope is a useful tool throughout the lab and for different tests, such as the transient tests like CS118 and 117. So, modern oscilloscope techniques for use with 461G. So this brings us to our final reason of our top 10 list. Let's think about smart broadband amplifiers and what they could do in your lab. And you know, making and meeting the field strengths that mill standard requires is not an easy task. And so, you know, certainly in the world of EMC, the mill standard testing is some of the more stringent in terms of what's required from the amplifier. And really, in order to do this, what you really need is an amplifier that has superior VisWAR performance, where you're going to get the nominal output power at 6-to-1 VisWAR, which is not a strange amount of VisWAR to get in some of the frequency bands as you do RS-103 for mill standard 461. So, you know, there are amplifiers out there that can help you meet some of the more challenging bands, like the low frequency band from 9 kilohertz to 200 megahertz. You know, think about maybe using a different type of technology, perhaps a liquid cooled technology, to help you meet that, and not having to inch in the transmit antenna to the point where you make the field, but actually be able to make the field at the 1 meter test distance that's required in the standard. And then maybe have a more modular design where you can add power and add frequency fairly easily in order to upgrade in the future. And then, you know, kind of an interesting approach is maybe having a tunable amplifier, where you could tune between a traditional Class A linear to a Class AB, where in low VisWAR situations, a Class AB can actually deliver more power, up to 50% more, depending on, again, the VisWAR that's coming back. So these all are approaches in a modern broadband amplifier, a smart broadband amplifier that you can actually talk to, and something to think about when you're considering upgrading your lab. So this concludes our webinar on the 10 reasons to update your mill standard 461G lab. Of course, I just wanted to briefly mention the fact that Roda & Schwartz is fully involved in the EMC testing world, and make a full portfolio of both EMI and EMS products that fit into the categories that we've talked about here. So please reach out to us if you have some direct requirements, and we will get involved in your application. So in addition to standalone products that we've talked about earlier in the webinar, just wanted to make sure everyone is aware that Roda & Schwartz is also fully capable of delivering a complete test system for EMC, for OTA, antenna test, and Tempest. So bear that in mind as well, and again, engage us with your applications. So this is the conclusion of our webinar. I wanted to thank our hosts again at Washington Labs. Please engage with us in the chat session if you have any questions, or contact us later on directly. And I want to wish everybody a great day, and please stay safe out there.
All right. As Jeff mentioned, we have reached our Q&A section, and at this time, I would like to introduce Jonathan Koch, who is an EMC application engineer at Roden Swartz, and he will be assisting Jeff with answering questions. So, Jeff and Jonathan, I will go ahead and read the question out loud, and then you will follow with the answer. Sounds okay?
Sounds good to me.
All right. Let's see the first question. Scrolling down. Okay, here's one. Are FFT receivers as accurate as a traditional EMI test receiver?
So we have many studies and can produce a white paper on this topic if anyone is interested. But as I said, the FFT receiver is a mature technology. It's been around for 15 years in some of our products. And, we have the studies to show that when you do either a step scan or a time domain scan or FFT mode, you have the same exact results. The correlation is extremely high. So there's no sacrifice for using the FFT receiver.
All right, let's see if I can find another question. Yep. Can I use the visual inspection software tool as a standalone software?
Yes. So these kinds of tools can run in conjunction with your EMC software, or can run as a standalone, and there are applications obviously for both, but it is independent, but with links to work in conjunction with the EMC softwares that are out there as well.
Jeff, one more thing to note is that Advise has the virtual camera mode where you can actually play back your pre-recorded videos, and Advise can analyze them at that time as well.
That's true. Thank you, Jonathan.
All right, scrolling down. How much power do you really need to make 200 volts per meter a 1 meter distance in the low frequency band?
So, Jonathan, do you want to talk about this, because you have experience both as a as a test engineer and obviously with Roda and Schwartz systems about making the field at the low frequencies.
And yeah, definitely, this seems to always be the big area of concern and topic for mil standard testing, is reaching that 200 volts per meter at a 1 meter distance. We have a couple products that have greater than 3,000 watts of output power, which can definitely help to be able to reach that 200 volts per meter. One of the other things is also, maybe like a portable anechoic wall that can help you tune the chamber a little bit if you're, missing a couple frequencies here and there. Typically, to do it at a 1 meter distance without, any additional input, 5 kilowatts is definitely what we recommend, and you should be able to get that over most of your frequency band in order to reach that 200 volt per meter requirement.
All right, thank you. I believe that is all the questions for now. I'm making sure. Hold one moment.
No problem.
Okay, I do see one more question. Why can't the real-time spectrum analyzer be used for official measurements?
So that's an interesting question. If you look at the way the architecture of a real-time spectrum analyzer versus an EMI test receiver, when you do the real-time mode, for instance, the real-time spectrum, the preselector is bypassed. So the preselection capability that was talked about in the seminar would not be allowed, and that makes conformance, right? Because you have these banks of filters that are part of the preselector. If you want a wide bandwidth in a real-time spectrum analyzer, you can't have those filters in front. And so the two, really for the EMI test receiver, that real-time spectrum analyzer is a diagnostic tool, not a tool that you can use with a full compliance test.
All right. At this time, I don't see no additional questions. But if for some reason I overlooked your question or you have a question later after this webinar, please feel free to send your questions to what you see on the screen, questions@wll.com, and a member from Roden Schwartz will contact you directly with your answer. So again, our thanks goes to Jeff Solomon for taking time out to enlighten us about 10 reasons it may be time to update your Mill Standard 461 test capabilities. Our next upcoming webinar is covering fundamentals of EMI on March 11th at 1 p.m. Eastern Time. If you haven't already done so, make sure you visit our website to register for this webinar if you're interested. On behalf of the Washington Labs Academy and Roden Schwartz, we would like to thank you all for attending. I'm going to go ahead and end the event, but please enjoy the rest of your day, and most importantly, please stay safe. Thank you all. Thank you, Jeff and Jonathan.
Thank you, everybody. Have a great day.
Thank you.